The next is pulse width modulation or pulse division modulation. So this will all even pulse frequency modulation. So these all are for same. We will call it as like a PWM. Normally PWM, or even we can say it as PDM, pulse division modulation, pulse width modulation. Even PFM is also correct because pulse frequency modulation. Actually here the width of the pulse will be changing in accordance with the amplitude of message signal. You know, all the analog pulse modulation schemes, the message signal is analog in nature. It is continuously changing over time. So, carrier is pulse. So, pulse width modulation means the width of the carrier pulse will change in accordance with the instantaneous amplitude of modulating signal. Next is pulse position mode. Actually, width and position is somewhat means nearby way. Pulse position modulation means the position of the pulse will change in accordance with the instantaneous amplitude of modulating signal. That is called as PPM. So now PAM, PWM and PPM. Now we will see how to generate PWM modulation and PPM modulation. So this is the circuit for generating pulse division modulation PDM and pulse position modulation PPM. Circuit consisting of a comparator is an op-amp circuit. Comparator is having two input. One is a non-inverting input, that is a plus terminal. Another one is an inverting input, that is a minus terminal. To the non-inverting terminal, we are applying our message signal. So this is the message. XT is the message signal. And to the inverting terminal, it is a sawtooth waveform. It is acting as a carrier here. Now, what a comparator will do? A comparator will compare its two input. Now, the non-inverting terminal voltage is higher than the inverting terminal voltage. The output of the comparator will be a high value, a positive high value. If the non-inverting terminal voltage is lower than the inverting terminal voltage, the output of the comparator will be a low value. So now we will see what is the output of the comparator. Now these are the two inputs. This is the message signal XT and this is the sawtooth wave. Say I will represent it as CT. This is the sawtooth waveform. Now what we have to do is we have to compare. These are the two inputs applied to this comparator. We have to compare these two inputs. Now look at this. This point, these two inputs meet. So from till there, starting from the 0 till there, you check which input is higher. Whether the blue color, that is the message, or the red color, that is the sawtooth. The blue color signal is higher, of course, because red is below that. Now the blue color signal is high means message signal amplitude is higher than the sawtooth waveform. So where is message signal? To the non-inverting terminal. So output will go to a high value, positive high value. Now, fine. Now see here, from here till here. If you are looking here till here, what is high? Blue or red? The blue is lower than red, that is positive terminal voltage is low, so the output is low. So normally I should draw it as a negative value, but here I am drawing for example only as 0 as the supply voltage may be of comparator is 0. Fine. Negative voltage is 0. Now look here, the third part. From here till here. Check here, the blue color is higher than the red. That means message signal XT is higher than the carrier signal. So the output will go to plus. So now this is the way we are generating a pulse, you can see by checking the output. The width of the pulse is changing according to the instantaneous amplitude of message signal. So width of the pulse is changing according to the instantaneous amplitude of message signal. This width and this width is not same because the amplitude of message signal is different. Now, so this will be the pulse division modulation. So that means the output of comparator what you are getting is pulse division modulation or PWM. Now, how will get PPM? When this output of pulse division modulation is applied to a monostable multivibrator, the output will be PPM. So now, what is a monostable multivibrator? When a trigger signal comes to a monostable multivibrator, it will provide a fixed width pulse at the output. So now here the trigger will be acting as your PWM signal. So each falling edge of trigger will come as the PWM signal. So now look, this is a falling edge of this PWM or PDM. So from in this falling edge, I will get at the output of monostable a fixed width pulse. Similarly, this falling edge, again I will get a fixed width pulse. So the width of the pulse will be same. So now here if you are observing, so this is called a PPM. The amplitude of instantaneous amplitude of message signal is changing, width of the pulse will change. The instantaneous amplitude of message signal changes, the width of the pulse will change. This is called PPM. See, in the next page, it is provided a clear picture with waveform. See here, this is your message signal. You can see continuously varying, and this is a sawtooth waveform. Each one you can check here. Look at this. If you are considering at this point, from to this point, which one is high, your message or the sawtooth? Message signal is high. If message is high, output will go to high. Now from this point to this point, no, till this point to this point, which is high, sawtooth is high, so output is negative. From here to here, message signal is high, so output is positive. So like that, if it is going, you will get the width of the pulse will change according to the instantaneous amplitude of message signal. Now that is the PWM or PDM. Now how we will get PPM? This signal will acting as the trigger for monostable multivibrator. So each falling edge of this will be acting as a trigger for monostable multivibrator. So this falling edge, I will get a pulse of fixed width. This falling edge fixed with the pulse. This falling edge fixed with the pulse. So now if you are looking, here the pulse is here. So distance between the pulses are not same. The position of the pulse is changing according to the instantaneous amplitude of message signal. This is called pulse position modulation. This is called pulse position. So now here you have a small comparison of, it's written as a comparison of PAM, PDM and PPM. You already studied in detail about pulse amplitude modulation, pulse division modulation and pulse position modulation. So just see the comparison. You know, this is a flat top sampled PAM. It is represented as the amplitude of pulses will change in accordance with the instantaneous amplitude of message signal. Here width of the pulse is changing and here the position of the pulse is changing. Now this one, width of the pulse decides the bandwidth. How much is the width? That will decide how much bandwidth is required. Here the rise time of the pulse decides the bandwidth. Here both, even in PPM also, rise time of the pulse decides the bandwidth. Here the amplitude of each pulses are different, means transmitter power is also changes because power is also depending on the amplitude of the pulse. But here all the amplitudes are constant. Transmitter power still varies because it varies because of the width also, because here width is changing. So transmitter power varies. But here the amplitude and width are same, means transmitter power will be constant. Now here the amplitude is changing, so it will be more prone to noise. So noise will be high. But here amplitude is fixed. Here also amplitude is fixed, so noise is minimum. Now this system is, because amplitudes are changing, means it is complex system. But this is simple system, this is also simple system. It's a comparison on PAM, PDM and PWM.